Okay, so in this video we're going to talk a little bit about measurement device precision. Okay, so when you use a measuring device of some sort in a laboratory, we need to know exactly how to evaluate the precision of that measurement tool, and also how does that determine how we record the the actual measurement when we are filling out a lab report. Okay, so I want you to imagine that we've got this object. Maybe it's a green bar. We encounter these all the time in lab, and we have some sort of a ruler, a measurement device that measures length, and it's in centimeters. And so this is just, I'm showing part of the scale, and this is just sort of a fictitious example, but it illustrates an important point. All right, so if we look at number one here, the statement says we can be certain that the object has a length between this and this, okay, centimeters. And so if we're kind of comparing the how long this green object is to the scale, and I think, would you agree with me that we can agree with certainty that this thing is somewhere between 40 and 50 centimeters long? Okay, I mean, you'd have to be sniffing glue not to agree on that. So we'll put those in. Okay, it's somewhere between 40 and 50 centimeters. However, we can do a little better than that, though, right? I mean, you can kind of, in your mind's eye, you can look at the scale and, sort of imagine that this is the midpoint, so this would be 45, and then you can even go a step further and kind of see little tick marks here, for every centimeter. So if you were really forced to estimate what the length of this object is to the nearest centimeter, what would you say? All right, so what would you write in here? Well, okay, so maybe 43, maybe you said 42, maybe you said 44, but 43 is probably in the ballpark, right? So that illustrates the act of estimation. Okay, so you can take a scale like this, which is only marked every 10 centimeters, and you can use your judgment, your powers of estimation, to interpolate between these two marks. Okay, so let's say we got 43. Now, in the process of doing that, this digit, the ones digit, is what we call the estimated digit. Okay, we could be wrong. I mean, it could be 42, it could be 44. We had to use our judgment. There was a little bit of subjectivity here, and so this is the last digit of any measurement is known to be an estimated digit. Okay, so that's an important important concept I want to emphasize. Okay, but we recognize that even though we're estimating it to be 43, we recognize that there's kind of this zone of what we might call confidence. So there's kind of a confidence zone where we're pretty sure it's between 42 and 44, let's say. Okay, and so when we do the final recording of the measurement, we're going to record this as the length of this green object as 43 centimeters plus or minus 1 centimeter. Okay, so any good measurement, scientific measurement, is going to have two components. One is your best estimate, and then you're going to give kind of a plus or minus, like a range, what might be called a confidence interval. And that confidence interval reflects how good our estimation was. Okay, so that's one example. Now let's say we upgrade to the deluxe model of our measurement tool, and now we've got not only every 10, but we've got every centimeter now has a tick mark. Okay, so when we kind of line it up and look at where the edge falls on the scale, here's 41, 42, 43. I think that, again, we unless we're crazy, I think we can all, get 10 people in a room. I think all 10 of us can agree that this object is somewhere between 43 and 44 centimeters. Okay, so we can be certain about that. That's a reasonable statement. But then we can do better, right? We can do better than say it's between 43 and 44. Again, we can use our powers of estimation. And so if you had to estimate to the nearest tenth of a centimeter, where would you put it? Okay, so you're using judgment, you're using your skills of estimation, and let's say it's like 43.5. All right, it kind of looks like it splits the uprights there. So we'll say 43.5. Now, in this estimate, the 5 is the estimated digit. Okay, because there's no tick marks there that are telling us that it is in fact 0.5. We had to use judgment, and so that is the estimated digit. Again, it's the last digit, the furthest to the right. Okay, and along with this comes its own interval of confidence, and we recognize that we're fallible, we have humility, and so we say, well, but it could be somewhere, anywhere in here, but we're pretty sure it's in there. So that's a confidence interval. And I think you can see that compared to the last one, this confidence interval is much narrower. Okay, and that's a reflection of this more, higher precision measurement tool. Okay, so then finally, when we go to record our measurement, we can say that it is 43.5 centimeters plus or minus 0.1. Okay, because we're estimating to the tenth of a centimeter. Well, we don't have to stop there. Let's say we get the super deluxe model, and we have lots and lots of tick marks here. Okay, so now all you got to do is just kind of line up the edge, and okay, well, that's kind of ridiculous. So again, the bar is the same. It's the same bar as the last two examples. We know it's between 43 and 44, but let's enlarge this a little bit so that we can see. All right, so if we had a magnifying glass, and then we actually labeled these little tiny tick marks. Here we have every tenth of a centimeter is marked with a scale. And so now if you kind of bring the edge, kind of with your eye, bring that down, you can see it is most definitely between 43.4 and 43.5. Okay, we can all agree on that as reasonable people. But we can go a little bit further, and we can estimate where in this 1/10 of a centimeter range is this length. Well, one reasonable estimate would be 43.42. Okay, so what I'm just saying, to my eye, it looks like it's about 20% the way between the 0.4 and the 0.5. Okay, and so it's a very narrow confidence interval. Now the 2 becomes the estimated digit. Okay, so if you were to see this measurement in a magazine, a science journal, a lab report, you would say that the 2 is the estimated digit. They probably had tick marks to the tenth of a centimeter. Okay, so the final measurement would be 43.42 plus or minus 0.01, right? Because now we're estimating to the hundredth of a centimeter. Okay, now I could go to the next slide and show you an even ultra super deluxe model with tick marks at the hundredth of a centimeter, but you get the point. This could go on and on and on. All right, and so the point here's like the deep truth. In a sense, you're never going to know the true length, the true value of this measurement, are you? Because it sort of depends on how precise your measurement tool is, and you can always get better, right? Okay, so let's summarize. So here we have, I've just placed the three measurement devices vertically, one on top of each other. And what I'm trying to show here is that as we go from, top to middle to bottom, you can see that we are increasing the precision of the measurement tool, right? I think, we can all agree on that. So that has implications for these three properties. Okay, our estimate, the number of significant figures, and the confidence interval. So with the first measurement device, we estimated the length to be 43 centimeters, and we we established that the last digit, the 3, is an estimated digit, right? The second device, we could estimate out to the 10th place, okay? And the 5 is the estimated digit. The most precise instrument, we could estimate to the 100th of a centimeter, and that made the 2 the estimated digit here, okay? Now, if you look at this measurement, the first one, I think you'll agree that there are 2 significant figures, right? And we kind of went over that in class. For the middle measurement tool, see how many significant figures we have? 3. And then I think you can see for the third most precise tool, there are 4 significant figures. So I think you see a pattern here, and I want you to know this. As the as the precision of the measurement device improves, typically this allows us to use more significant figures. All right, so this is where significant figures come from. And then finally, the confidence interval. All right, for the first one, it was plus or minus 1, and that zone of confidence was a little bit wide, right? And then it was 0.1. So the confidence interval was considerably narrower. And then finally, with the super deluxe measurement device, we were able to bracket, that is, narrow down the range of possible lengths to a very small interval. Okay, and that's what better and better precision does for you. Is it allows you to narrow down that range of certainty. Or high confidence, I should say. Okay. All right, last slide, just to kind of wrap it all together. So in terms of concepts, what I want to get across to you is the precision, what I call MD, measurement device. The precision of a measurement device is a huge, important quality of a measurement tool. And the level of precision sort of determines the number of significant figures that one can report when you're recording measurements, and it also determines the confidence interval, how small that is. And so, again, to tie it all together, as the level of precision improves or increases, so do the number of significant figures that you can report, with a straight face. And that decreases, it narrows the confidence interval. Okay, you can specify to a more and more precise level, what the actual value is, the true value. I guess I keep summarizing. I'm sorry. One more. So here's what scientific measurement provides. It gives you an estimate of the true value. All right, but you can never really know the actual true value. It just gives you an estimate, and then it also provides a confidence interval around the true value. Scientific measurement does not provide the true value of a property, and the exception here is counting. So, if there's 10 or 100 objects in a collection, in science, it's agreed that if you count carefully, you can consider that number to be true and exact. Okay, and don't forget, measurement requires good judgment, and that comes in, with the estimation. Okay, thank you very much for watching, and I'll see you guys soon.